We have finally come to the last set of videos as far as linear algebra is concerned. So I'll be having four more videos starting from this one, and we'll be talking about some advanced and applied linear algebra. Okay, so in this case, I'll be looking at linear algebra in data science. We've seen all of that here and there along the line, but I just want to focus on this a little bit more, talking about how linear algebra plays into data science because I mean, data science is something I really care about, and it is always lovely to see how some core math concepts play into some of these practical areas. So let's go ahead and talk about linear algebra in data science. First of all, we talk about feature spaces, principal component analysis, and regression. This lesson explains how linear algebra supports data science through feature spaces, principal component analysis, and regression. And we'll see some worked examples as usual. So straight up, we talk about why linear algebra in data science. Why do we have to talk about linear algebra in data science? First of all, linear algebra helps us to represent data as vectors and matrices. That's one thing we've seen all along. And it helps us to measure similarity, to reduce dimensions, to build predictive models, and optimize learning algorithms because it's all about, maybe reducing error and getting the best results we can get under whatever constraints we might have. Then most machine learning algorithms are built on, of course, machine learning is an integral part of data science. So that's why, so when you see machine learning, it is actually representative of data science. So most machine learning algorithms are built on vector spaces, matrix operations, projections, eigenvalues, and eigenvectors. And these are concepts you already saw in linear algebra. So you see that linear algebra is a bedrock for machine learning and largely data science. So let's talk about feature spaces. So when we build of course data science uh starts from maybe simple things like working with Microsoft Excel, and then you can scale that up and you begin to talk about data visualization using things like Power BI or Tableau, and of course or even Excel itself, and then you can go to Python and still do data analysis with that, and even advance to go on to the idea of data science where you begin to look at machine learning, which is subdivided into some other areas. So in all of these things, you are working with data and you work with variables in your data set, and these variables are called feature, right? So a feature is a measurable property of data. Examples of variable may be things like people, information about people. Maybe you have a data set where you're looking at age, height, and income, and you want to see how all of these things play in an economy. Then maybe you're talking about houses, maybe households now. Maybe you are a rural sociologist or something like that. So you want to know family sizes, the locations, house prices, and things like that. You want to see how all of this work together. Or even in working with text, maybe word counts. So maybe you want to see, maybe you want to carry out an experiment in different locations, and you want to try to estimate how many words specific people speak per day. And from there, you want to be able to say, to maybe say, maybe there are significant differences between the number of words men and women use in a day and things like that, right? So that's the idea of a feature. So in all, we say a feature space is the space formed by all features. So if you have a data set where you talk about maybe you are interested in the body mass index of a group of people. So in that case, of course, you need to know their heights, you need to know their weights. Of course, we also want to know their age to know to maybe to see how all of this relate together. And then so all this age, height, weight put together, each of them is a feature. All of them put together is what we call a feature space. I know in linear algebra we talk about spaces a lot, right? So when we talk about dimensions of feature spaces, if a data set has one feature, then that can be represented with a real line. Maybe you just are talking about the height, right? So that's a one-dimensional real number space. But if you have two features, maybe weight and height, right? Weight and height, which are necessary to compute the body mass index. So now you're talking about a plane, which is two-dimensional real number system in that case. Maybe then you're now talking about width, height, and age. So it goes three-dimensional space like that. So and you can have more. So you can have an n-dimensional space system depending on whatever you have. So each data point is a vector in this space. All right. Each data point is actually a vector in this space. So let's look about vector representation of data. Suppose we have age, income, and education. So one person can be represented as X. So based on age, income, and education, and that belongs to the three-dimensional real number space. So you can represent that like that. Then you can also have a data set. So one data, so the X now is the information about one person. That's like maybe one row, age, income, and education. For one row like that, that you have information about one person. Then you can have a data set which becomes a matrix. So you now have information about the first person, second person, up to the nth person. So that becomes your whole data set now. So the information about one person, each x1, x2 is like a data point. Like what you have here now, you now have it in many rows like that. So the rows are the samples. That's each information about each individual, and the columns are the features. So for each person now, then you have age for everybody, education level for income for everybody, education level for everybody, and things like that. And then we have the idea of distance and similarity, and this is very useful in things like large language models. These are like basic uh, building blocks for LLMs, which have led to all this generative AI and all of these things, right? So we talk about distance and similarity. First of all, we have Euclidean distance. That talks about distance between two data points, for instance, and it is given a summation from I equals 1 to n of xi minus yi all squared. So this measures straight line distance, right? And then that leads us to cosine similarity, where you have cos theta to be equal to the dot product of x dot y all over absolute value of x over absolute value of y. Of course, it's more like when we talked about dot product, it's the same thing as x dot y being equal to modulus x modulus y multiplied by cos theta. So this measures angle between vectors, and it is used in text analysis and recommendations, because the whole generative AI thing is all about prediction, like probability with which one word follows the other. And this all this cosine similarity determines how that goes. So, and then we have an example of a feature space, right? Imagine that you have two features. You're looking at study hours x1 and sleep hours x2, and you have a student A whose study hour is 4 and the sleep hour is 6, while student B, the study hour is 7 and the sleep hour is 5. So what do you do in that case? You can find the distance apart of these students, like in form of some kind of magnitude, and then you say D is square root of 7 minus 4 squared. That's x1 minus x2 plus 5 minus 6 squared, and that gives like 9 plus 1, and that's root 10. So the students are root 10 units apart. So this is like the magnitude of separation between these students. If that is a measure of maybe their performance or something. So the question now is, why do feature spaces matter? Feature spaces determine how data is seen by models, how easy patterns are to find, and whether classes are separable. So better feature spaces lead to better learning. So in a feature space, right, you want to be sure the most important features are there. And that's why we have something like feature importance in machine learning. So there we have some algorithms to say, oh, of all these features, these are the most important ones. And some features, they are collinear. I think that's the word. They behave the same way. So those features can actually they may not be able to give you good results. So you want to remove features that behave the same way so that you can actually know what is really contributing a lot into a whole setup you have in your data. Okay, then that takes us to the idea of principal component analysis, which is a very powerful tool in data science. So real data sets often have many features. I mean, I was just talking about that. And as a result of that, you may need to zero in on the features that are really very important. So real data sets often have many features, correlated variables, like features behaving like the same, and then noise, like some data that don't really contribute, so that disturb the performance of the data. So PCA now, principal component analysis, reduces dimensions while preserving important information. So it can filter out some noise, remove some things that may not be necessary, and preserves the key information. That's the job of PCA. So the intuition of PCA is such that it finds new axes that capture maximum variance that are orthogonal. You see orthogonality coming into this now. So because yeah, you can look at these whole features as vectors. And then it's also remove redundancy. We talked a lot about the idea of independent vectors. So when vectors are when one vector depends on another, it's actually redundant because it captures the essence of that vector would have been captured by another vector that represents it. So PCA helps to remove such situations to be sure that what we have, that any feature you have is actually talking about, they really are important to the behavior of the system you might be considering. So you have original axis like x1, x2, xn, and by the time you do principal component analysis, you have new axis like principal component 1, principal component 2, all the way down to principal component n. Now, interestingly, the principal component 1 captures the most variance. It gives the most information, right? Other levels, the information what we capture at PC1 will not be as serious as um what to be captured at other levels, right? I mean, PC1 captures most information, so PC2 doesn't capture as much as PC1, and so on and so forth. So we talk about the geometric view of PCA since we see that geometry now is leading to even working with data science, right? Geometric view of PCA. PCA works by centering the data, rotating coordinate axis, aligning with data spread, and removing weak dimensions. And this is a change of basis. So you see, change of basis is how, so the PCA works based on the idea of change of basis by centering data, rotating coordinate axis, aligning with data spread, and removing weak dimensions that may be a distraction in the data set. Okay, so talking about the mathematical steps of PCA now. So first of all, given a data matrix, so you have X like, which represent the feature space in M by N, a real number system. So the first thing you want to do is to center the data. So you have XC, which is the same thing as X minus mu, right? So you are extracting the mu, so you can get the center of the data, and then from there you have the covariance, which is computed as 1 over M, M by N, right? 1 over M XC transpose XC. You get the covariance from there. And then from there, you get the eigenvalues. So eigenvalues, which talks about the fact that, when a matrix acts on a vector, it ends up scaling that vector, right? And then you go ahead and talk about projection, which we talked about projection a lot under orthogonality. And you have Z. So you can see all the concepts coming together, all the concepts of eigenvalues, the concept of orthogonality and all that. So you have Z equals XCVK because you're projecting, you're projecting things like that. So here VK contains top K eigenvectors. So these top K eigenvectors now will now be like your most important features like that when you do the projection because you would have removed all the unnecessary things from that. So let's look at an example what PCA does in 2 dimensions. Imagine you have a data 2, 1, 3, 2, 4, 3, 5, 4. All right. So in x1, x2, x3, f are 2, 3, 4, 5. And then all your y's are 1, 2, 3, 4. So the average of the x is that's 2 plus 3 plus 4 plus 5. That's 14 divided by 4. That's 3.5. And for y, 1, 2, 3, 4, that's 10, I believe. Yeah, that's 10 divided by 4. That's 2.5. So then you center them. The first thing is centering. So what's the centering about now? So you have 2 minus 3.5. You get minus. So for all the x values, original x values, you subtract 3.5. That's why the first one is 2 minus 3.5 minus 1.5. 5 minus 3.5, you have 1.5. Then you also center this one. So by removing the average, you center all this. The next thing is you go for the covariance. So for the covariance, now we saw the formula the other time. That's 1 over M XC transpose XC. And if you do that for this now, you get 1.25, 1.25, and all that for the covariance all across. Then you can then get the main eigenvector V1, which is 1 over root 2, 1, 1, right? So, and we see that the data lies mostly in one direction. So, having the two directions don't really help. So this simple thing now has shown you that the data lies mostly in just one direction, which is the main eigenvector. So, what are the benefits of principal component analysis? So, first of all, when we talk about compression, compression removes redundancy. So it's more like when you remove vectors that are that are multiples of the others, right? Because the essence of that vector would have been captured by another vector. So you can compression removes redundancy. Then you have speed, which lowers dimension. The noise reduction removes weak signals, and visualization enables 2D and 3D plots like that. Then that takes us to the idea of regression. That's another application. So far we have seen that in data science, right? Linear data science has its place in dealing when we in capturing feature spaces. I mean, linear algebra helps in data science by capturing feature spaces, and then it helps to reduce data set dimension through principal component analysis. And now we go to the idea of regression. So regression is another very useful tool, one powerful machine. I mean, it's like one of the simplest machine learning algorithms, regression. So regression models relationships between variables, and the general form is y approximating f of x, which we already saw, like talking about things like least square uh, and all that. So we have linear regression, y equals omega w transpose x plus b. It's more like the ax plus b we saw the other time, except that this w transpose now is matrix. So where w transpose is weights and B is the bias, right? So from there now we can have a matrix form of regression where we have X to be X1 transpose, X2 transpose all the way down, and we have Y to Y1, Y2 all the way down, and then you can have your model to be Y equals XW plus epsilon, epsilon being the error. So we come up with the idea of least square principle, which you saw already under uh orthogonal projection, and we saw how that plays into least squares. So we minimize the error. You minimize the error such for the norm xw minus y all squared. So this finds the best approximation you can ever get, and geometrically it is actually a projection. That's why we saw orthogonal projection and least squares the other time. So, and then you have your normal equations. You remember in cases where you have inconsistent equations where you have more, you have more equations then you have variables. So you have inconsistency. So least square via normal equations can help you take care of situations like that. So the optimal solution is W, which is X transpose X inverse X transpose Y. We did something like this previously. So this exists if X transpose X is invertible. So as far as you can find the inverse of this, then you can actually estimate, you can approximate the value of W. So the deal now is want to find the geometric interpretation of regression. First of all, from this setup here, we see that y is the target vector, right? Y is the target vector because y is a function of x, so to speak. Then xw is the prediction. Then we project y onto the column space of x. And that's all that is happening there. And then we see that regression is actually orthogonal projection that we've been doing before. So a very good simple example of simple regression. You have, I think we've dealt with this a whole lot. You have 1, 2, 3, 2, 3, 5, which you can represent as y equals w1x plus w naught. So for the design matrix now, you have 1, 1, 1, 1, 2, 3. That's for the design matrix. And then y on the other side, on the other hand, is 2, 3, 5. So if you now solve the example, you have 3, 6, 6, 14, and then you have 10, 23 like this. And then that ends up giving you 0.33, 1.5. And then the final model is now 1.5x plus 0.33 that way. Okay. So with that in place, then we have you can have multiple linear regression where you have for many features, right? You can have y equals w1 x1 plus w2 x2 plus w nxn all the way down. So this represents a hyperplane in n-dimensional real number system. So now what happens when x transpose x inverse does not exist? So there are cases where x transpose x inverse does not exist. In that case, you have to if that happens, if X transpose X is singular, singular meaning that the determinant of the matrix is zero, so that means it is not invertible, then you have to use pseudo inverse via SVD, or you can talk about ridge regression, gradient descent. Interestingly, I have a playlist, I think quite extensive playlist on numerical optimization techniques. We have taken care of all these support vector, SVD, what's support vector, something, I've forgotten what is D is about. Support vector, uh, man, too many things. SVD. Yeah, support vector decomposition. Yeah. So I have all these things, ridge regression, gradient descent, and all that. So this stabilize learning actually. So even when there's no inverse, you can use all these other concepts. So let's talk about connections between topics now. So we have feature spaces representing and their role is for vector representation, PCA for eigenvectors and projection, regression for least squares projection, and all this rely on linear algebra. So linear algebra is at the background of most of these concepts. So in summary, we see that feature spaces for feature spaces we see that data act as vectors, and we have geometry of learning. For PCA finds main directions. So if there are too many directions for a data set, so PCA helps you to narrow down on the directions that really matter. And then they reduce dimensions and removes noise too. Then for regression, they solve linear systems, project targets, and minimize errors. Okay. So linear algebra is the foundation of data science. In essence, that's what we are saying. So you can try your hands on some of these questions. This first one says, okay, maybe we can show them in twos. So problem one, feature vector. A data set records height, weight, and age. Write the vector representation for a person who is 170 cm tall, weighs 65 kg, and 20 years old. I mean, you just have 170, 65, 20, just like what we had before, in a vector form like that. So, so it's more like HWA, it's more like doing something like HWA, okay, and that is height 170, right? So you have 170, 65, 20, okay, 170, 65, 20. Easy. So something like that. So you see, all this information can become like vectors, and then you can work with them once you can transform. So a data set contains 12 features. In what space does each data point lie? So in what space? So because there are 12 features that we say it's a feature space, and that will be like and then a 12-dimensional feature space, like a hyperplane. So how many dimensions does this space have? Of course, that's 12. Uh, how many dimensions will this have? Mm, yeah, 12 dimensions. Can we say that? Then Euclidean space now. Given two vectors, this compute the Euclidean distance between x and y. Of course, that will just be square root of uh 4 squared minus 2 squared, 1 squared minus 5 squared, 3 squared minus 1 squared, all the other way around. Then we have cosine similarity. Compute the cosine similarity between x and y. So that's cos theta now. So you have cos theta equals uh, x dot y all over the modulus of x all over the modulus of y. All of that can go. So that's 1 times 2, 2 plus 2 times 1, 2 plus 2 times 2, 4. That's 2 plus 2 plus 4. That's 8 all over modulus of each now. Square root of 1 squared plus 2 squared plus 2 squared. That's square root of 9. That's 3. Square root of 9 again is 3. So that's like, what do we get there now? So that'll be 8 over 9, I think. Cos theta is 8 over 9. So you find 8 over 9 and take the cos. So that's the cosine similarity between x and y. So compute data matrix. Three students have scores 80, 70, 90, 85, 75, 60. Write the data matrix. Write the data matrix X and state the shape of X. So that, I mean, that looks like it to be 2 by 1 in that case, you know. Then you have a no, 2 by No, that'll be 3 by 2, right? 3 by 2, 3 rows, 2 columns. Because if you're going to write the X now, you have 80, 90, 75, then 111. And then the Y will be 70, 85, 60, or anyhow you want to represent that. So PCA centering, given this data, now find the mean vector, write the centered matrix. So the mean vector will be 2. For X, you have 2 plus 4, 6 plus 6, 12 divided by 3. That's 4. So you subtract 4 from each one, and you get the centered matrix. 4, 6, 8. You have 10, 18. divided by 3, that's 6. So subtract 6 from each one, then that gives the centered matrix. So, so the mean vector will be the pair of the mean of both. So for this is 6 over 3. I mean 6 plus 6, 12 over 3. That's 4 by 6. That's the mean vector. Centered matrix is when you subtract this 4 from each here, 6 from this. Then 7 now, covariance matrix. Use the centered data from problem 6. Compute the covariance matrix using this formula right here. Then you have PCA interpretation. The data set has eigenvalues. Lambda 1 is 8, lambda 2 is 2, lambda 3 is 0.5. Which principal component is most important? Of course, lambda 1 is most important because it carries the most information. So how much total variance is explained by the first component? Uh, okay, I think maybe that will be 8 over, so maybe 8 over 10.5%. That's how much that can explain because that's what the eigenvalue is telling us. Then 9, so for question 9, simple linear regression, you have 1, 2, 3, 1, 2, 2. Fit the model. I mean, we've done that a couple of times, so you want to try that out. So you write your x as 1, 2, 3, 1, 1, 1, and then your y is 1, 2, 2. Then you're looking for W1, W naught, and then you fit that. So least squares geometry, explain in your own words. What does it mean to project y onto the column space of x? So basically, it's more like you're projection is more like you're redirecting vectors to be perpendicular. So you're projecting, right? What does this give the best? Why does this give the best linear approximation? Yeah, because it's more like you're straightening out a bent vector, and then that way you would have minimized the error as much as possible. So yeah, I still have 3 videos to go. I'll be talking about linear algebra in some other domains. So watch out for that. And with those, after those 3, I would have come to the end of linear algebra, except something else comes up I need to talk about still. So thank you so much for listening. This is the end of this video. Let me know how helpful this is for you. Try your hands on these practice problems and let's see how well you get the gist. Okay. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. Um, if you have subscribed already, I thank you very much for that. If you haven't subscribed, what exactly are you waiting for? Go ahead and subscribe. Hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel, and that gives you some special privileges like you getting to see some videos before other people, or only you seeing some videos that others don't see. Only members get to see those videos. Um, you know, we can hang out, we can hang out together to discuss whatever interests you on this channel. Ultimately, you should comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.